In this series of videos, we're going to calculate inverse trig functions. First, let's recall what inverse functions are. Inverse functions are when you interchange their domain and range. So inverse functions interchange their domain and range, which means the inputs for one function become the outputs for its inverse. So recall that domain is your inputs and range your outputs. That's really important, knowing that definition of inverse functions. And that's really going to be the crux of working with inverse trig functions. These functions are symmetrical about the line y equals x. So you may recall that in working with inverse functions. When we have a quadratic function, its inverse, polynomial functions, rational functions, square root functions. But for a function to have an inverse function, remember that it must be one-to-one. That means that it has to pass the horizontal line test. And why it needs to pass the horizontal line test is because the y values won't repeat. So the y values will not repeat. So I'll show you some visual examples. First, we'll start with an example of a function that is one-to-one. So you might recall this function. This function is y equals x cubed. This is one-to-one. And the reason it's one-to-one is because the range goes down to negative infinity and up to positive infinity, and none of the y values are repeated. You might be thinking, okay, well that makes sense, but what does it look like when the y values do repeat? When the y values do repeat, we might have something like a quadratic function. So this would be the graph of y equals x squared. This is not one-to-one. The range of this function goes from 0 to infinity. So 0 to infinity, and all of its y values repeat except for the vertex. So let me show you. This y value of 1 repeats. You get an output of 1 when you put a negative 1 in and when you put a positive 1 in. So that y value of 1 happens twice, once when you put in a negative x, a negative 1 for x, and the other time when you put in a positive 1 for x. The same thing with every other value. Now, it only has to repeat one y value for it not to be one-to-one. So it only has to repeat one y value for it not to be one-to-one. But in this case, a lot of y values repeat. Therefore, it makes it easy to see that it is not one-to-one. Now, when we talk about the horizontal line test, let me show you. The horizontal line test, I can pass a horizontal line through the entire function on the left, and it only crosses through that horizontal line once. However, on the right here, the graph passes through the horizontal line once at that tangent line at the vertex, but then once I move that horizontal line up, it crosses through, the graph crosses through that horizontal line 2 times, and once it passes through more than once, It's not one-to-one. So it fails the horizontal line test. The reason it's going to fail the reason why we look at the horizontal line test is because, remember, this graph is going to be symmetrical about the line y equals x. So here's the line y equals x. So for it to be symmetrical about the line y equals x, we rotate it 90 degrees. So the green curve is the inverse of the red curve. However, the green curve is not an inverse function. And the reason it's not an inverse function is because it's not a function. It fails the vertical line test. So a function that fails the horizontal line test will have an inverse that fails the vertical line test. So functions have inverses, but for a function to have an inverse function, it has to pass the horizontal line test. It has to be one-to-one. So let's look at our inputs and outputs. Let's say that I were to take half of the parabola. Let's say that I only have this half of the parabola right there. So we have 0, 0, we have 1, 1, and we have 2, 4. The inverse function is going to, let me try and draw that a little bit better. It's a little bit better. It's going to be symmetrical about the line y equals x. So this is the line y equals x. So even if I just have these ordered pairs and I wanted to draw the inverse function, let's be very clear, this red curve does have an inverse function because the red curve passes the horizontal line test. To find the inverse without using an equation, I can simply reverse the inputs and outputs. So 0, 0, 1, 1, and then 4, 2. So we've worked with inverse functions before. Hopefully this was a good reminder. The reason why we need this reminder is because we're going to work with inverse functions for sine, cosine, and tangent. I'm going to start with cosine. I'm going to start with the graph of cosine. So cosine 2, 3, 4. Cosine is going to look something like this, right? So there's one cycle of our cosine function. I'm going to draw another cycle. Let me draw this one a little bit better. There we go. I'll come back and label. So hopefully you remember this graph. This is a really important graph. We have 0, 2 pi, pi, and then right here we have pi over 2, and right here we have 3 pi over 2. To the left we have negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Oops. Negative 2 pi. There we go. So this clearly fails the horizontal line test. So this is the graph of y equals cosine of x. It clearly fails the horizontal line test. However, we're going to limit the domain. Just like we took the quadratic function and we just cut it in half, we just used the piece that we needed. So we just used the half of the graph that got all of the domain, or all of the range from 0 to infinity. So it included all of the outputs from 0 to infinity. It just didn't include the repeats of those y values. So we cut it in half. We limit the domain so that it does become 1 to 1, and then we can create that inverse function. Same thing here. We need to make sure that we get all of the range. So the range goes from -1 to +1. We want to include all the outputs, but we don't want the repeats. So we're going to take this part of the function right here. Take that part of the function. So we're going to take the domain from 0 to pi. The range will give us all of our outputs from -1 to +1. This little section here will pass the horizontal line test. So with that domain in mind, the inverse function is written like this. Its domain is going to be -1 to 1, and its range will be 0 to pi. Now let's talk real quickly about what we have here. Y equals the cosine of x. We input angles into our cosine function, and our output are ratios. When we have y equals the inverse cosine of x, we're no longer putting the angles in. We've reversed the inputs and outputs. So our outputs are angles. Our inputs are the ratios. So that's really, really, really important right here. This information, really important for you to try and absorb. There's another way that we can write the inverse function. So we can write y equals the inverse cosine of x, or we can write y equals arc cosine of x. That means the same thing. Our inputs are ratios, and our outputs are angles. Now I would make some flashcards to remember the domain and range, because that's going to be really important. Our domain on the front, y equals inverse cosine of x, and the domain are your ratios, which is -1 to 1, and your range for y equals inverse cosine of x is 0 to pi. Now with that 0 to pi, I would also draw a picture. I would draw a partial unit circle, 0 to pi. Now the reason, or where that comes from, is that we limited our domain from 0 to pi. So if you look back here at the graph, our domain starts at 0 and ends at pi. Starts at 0, ends at pi. So if we translate that to the unit circle, starts at 0, ends at pi, all of these angles are legitimate outputs. Legitimate outputs. Look right there. Legitimate outputs. The angles are outputs for your inverse cosine. So we draw that picture because it's going to be really helpful for you to see that inverse cosine is going to give us outputs that are angles in quadrants 1 and 2. In quadrants 1 and 2. Now remember, cosine ratios are positive in quadrant 1. Cosine ratios are negative in quadrant 2. So that's going to get all of our ratios. Remember, this ordered pair is 1, 0. This ordered pair is negative 1, 0. Cosine is your x value. So you're going to get all of the outputs from negative 1 to positive 1 for your ratios, for your cosine function. Therefore, all of those outputs become inputs into the inverse function, giving us angles in quadrants 1 and 2.